1 minute, ma'am.
Okay. Ma'am, shall we start the session, ma'am?
Yes, ma'am.
Okay, ma'am. Happy evening to all gathered here to the 5 days online faculty development program on research methodology and data analysis for faculty and research scholars, organized by Department of Computer Science and Computer Application in association with IQAC. It's my pleasure to welcome all the participants for the 5 days online FTP program. I request all the gatherings to unmute your video for a photo session. I request all the gatherings to unmute your video for photo session. Thank you all. Every thought you produce, anything you say, any action you do, it bears your signature. Now I request Mr. C. Krishnan, Department of Computer Science, to give a welcome address.
Good evening to all the participants. We welcome you all for the 5 days faculty development program on research methodology and data analysis. I take this opportunity to welcome today's resource person, Dr. L. Sivagami, Assistant Professor, the Department of Mathematics and Statistics, SRM Institute of Science and Technology, Katanguluthur, Chennai. She has 9+ years of experience in the field of teaching from various institutions. Our eminent resource person has published 10 different articles in various reputed journals. She has presented many papers in international and national conferences. She has attended many workshops, seminars, and conferences. Madam has received so far 4 achievement awards in various fields. Once again, we welcome you, Madam. It's time to hand over the session to our eminent resource person, Dr. L. Sivahami.
Thank you, sir.
Please, Madam. Yes, Madam. Thank you, Madam.
Thank you, sir. Everything is theoretically impossible until it is done. Now I call upon our today's resource person, Dr. L. Sivagami, Assistant Professor in Mathematics, SRM Institute of Science and Technology, Katangulathur, to lead the session. Today's topic is fluids and their properties. Ma'am?
Yes, ma'am.
Okay.
Thank you, ma'am.
Thank you, ma'am.
Is it visible, ma'am? Is my screen is visible?
No, ma'am.
Okay, 1 minute, ma'am.
Okay, ma'am.
Now, is it shared, ma'am? Is my
Yes, ma'am. Now it's visible, ma'am.
Yes. Good afternoon to one and all present here. I thank everyone, the Department of Computer Science and Applications, to the St.Joseph College of Arts and Science for giving me this opportunity to present my topic in the field of fluids and their properties. I am Dr. L. Shivagami, Assistant Professor in the Department of Mathematics and Statistics from SRM Institute of Science and Technology, Katangulathur. Before going to see the various topics under the fluid, let us start from what is fluid. Actually, a fluid cannot resist a shear stress by a static deflection, and it moves and deforms continuously as long as the shear stress is applied. So if I tell the definition, it won't be easily recognized by everyone. So I think all of you know what may be the fluid. Fluid may be in the form of water, air, etc. Right? So all of us know that without water, we cannot live in this world. And then 75% of the earth is occupied only by water and 100% with the air. So that's why the field of fluid dynamics exists based on the water with air. So the fluid mechanics is the study of your water and the air in the terms of fluid mechanics, in terms of its Newtonian and non-Newtonian fluids. So fluid mechanics is a study of fluids either in motion or at rest. Both liquids and gases are classified as fluids.
Ma'am, excuse me, ma'am.
Yes, ma'am.
Now only your screen is visible, ma'am.
1 minute, ma'am. Okay, now is it visible, ma'am? Yes, ma'am?
Yes, ma'am.
Yes. Okay. Shall we proceed?
Ma'am?
Shall we proceed, ma'am?
Yeah, you can proceed, ma'am.
Yes. So fluid mechanics is a study of fluids either in motion. If we study the motion of fluids, it is called fluid dynamics. If we study the fluid in the resting form, it is called fluid statistics. So there are two main branches, which are fluid dynamics and then fluid statics. Fluid dynamics is the study of motion about the liquids. And if we study the same liquid or the fluid in the resting position, it is called fluid statistics. And both liquids and gases are classified as fluids. The theory available for fluid flow problems, but in all cases, it should be backed up by experiment. And it's a highly visual subject and with good instrumentation nowadays. In engineering and the human activities, we are having so much of applications, including medical field also. That is the studies of breathing and blood flow, oceanography, hydrology, energy generation. The other engineering applications include the turbines, pumps, missiles, airplanes, etc. So the basic equation of fluid motion are too difficult to apply the arbitrary geometric configuration. So that's why in most of the textbooks, we are having only the circular pipes, parallel pipes, vertical pipes, and then slanting pipes, etc. Because we cannot apply all the arbitrary geometric configurations. So it is possible to apply only the numerical techniques to complex geometries. So our focus is only the theoretical approach in this course in the engineering field. Before going to study the different types of your fluids, let us see the brief history about the fluid mechanics. In ancient days, there are so many mathematicians or physicists who developed the theory of fluid mechanics in terms of its applications in their day-to-day life. For example, I think all of us know the Archimedes who postulated the parallelogram law of addition and vectors in terms of its mathematics. Actually, all of us know that Archimedes found the principle of floating and submerged objects. Only based on that his principle, we have developed the ships and then the immersed objects, etc. Because the buoyancy effect, which occupies the throughout the fluid mechanics paper, which he found in terms of the floating and submerged objects. Because if you immersed any object or any product or any particle, anything in the full tank, the equal amount of water will be exited right from the tank. So that this for equal and opposite direction, there will be one force. That force is called the buoyancy force under the fluid. So that fluid, without that buoyancy effect, there is no fluid dynamics, and it was first developed by the Archimedes in the before 200 BC. After that, in the year 1450 to 1590, Leonardo da Vinci stated the equation of conservation of mass in one-dimensional steady state flow. Because only in the later 19th and 18th centuries, we have developed the one-dimensional objects into 2, 3, and then the four-dimensional objects. So in the period of 1400, Leonardo da Vinci found the equation of conservation of mass in one-dimensional steady state flow. Because at that time, he may have seen the stars, with otherwise the waves or jets or something in terms of starting from one place to another, moving one place to another. So he developed the study of one-dimensional flow, and after that, after 100 years, Edmund Marriott built the first wind tunnel tested models in it. Later on, in the year 1600, Isaac Newton postulated his laws of motion and the law of viscosity of linear fluids, now called the Newtonian fluid. So only the Newtonian and non-Newtonian fluid was discovered only by Newton in the year 1600. The theory first yielded the frictionless assumption, which led to several beautiful mathematical solutions. So the entire study of our fluid dynamics depends upon the Isaac Newton's postulates. And in the year 1700, Leonardo Euler developed both the differential equations of motion in the integral form, now called the Bernoulli's equation. Because entire study of the fluids depends upon the first derivative and second derivative, let us call it as dy by dx and d squared by dx squared, which is the differential equation, and later on it is converted into the partial differential equations. So we cannot solve everything directly. There is some critical problems in geometric configuration, so we need some mathematical problems. So it was developed by Freud in the year 1800. The laws of model testing and law Rayleigh proposed the dimensionless analysis. So all the key terms, whatever I uttered, everything comes under the fluid. So the fluid is entirely based on these properties. After that, in the year 1800, Reynolds published the classic pipe experiment and showed the importance of the dimensionless Reynolds number named after them, because the Reynolds number, only based on the Reynolds number, we are going to study what type of fluid is this one. Whether it will be the rotational flow or irrotational flow, or whether it is a laminar flow or turbulent flow. Because only based on the Reynolds number, the pattern of the flow will be vary. After that, in the year 1785 to 1800 and 1900, Navier-Stokes, the mathematician who added the Newtonian viscous terms to the equation of motion and the fluid motion of the governing equations. Nowadays, we are using only the Navier-Stokes equations throughout, whatever be the liquid or whatever be the fluid, either it is a Newtonian or non-Newtonian, whether it is compressible or incompressible, everything depends upon only the Navier-Stokes equations. Actually, he pointed out the fluid flows with the small viscosity, such as water flows and air flows, which can be divided into thin viscous layer near solid surfaces, or the interfaces are nearly in the invisible layer, or in the he developed it. The concept of fluids are actually, there are two different one is the liquid and another one is the gas. The liquids are composed of relatively close packed molecules with strong cohesive forces. Liquids have a constant volume and will form a free surface in a gravitational field if the unconfined form above. There is the fluid. The fluid is a substance that changes its shape if the force is applied on it. It has no shape of its own. It takes the shape of the container, and the liquids and gases are fluids. Because we all know that the liquefied petroleum gas, which is in the form of liquid in our day-to-day life, in our kitchen, in the cylinder. So the liquids and gas, both are fluid. And we are going to see some interesting fluids, which is a solid, which will be very interesting. And then now I will tell you, the properties of fluids entirely depends upon the temperature and the density and then the fluids. Actually, in each department will call the fluid in their own names. In physics, fluid is a liquid or it may be a gas. But generally, it is a liquid. So the physicist, the department of this, they are calling it as a liquid and then gas or any other material that continuously deforms under an applied or shear stress or external force. Also, the fluid generally includes both the liquids and gas phases. Its definitions vary among the branches of science. One interesting property, some substances can be both fluid and solid. Example, the silly putty. Silly putty, which looks like a toy. Silly putty is actually fluid, but it is in the form of solid. So this is a special case. Silly putty is a toy based on the silicon polymers that have unusual physical properties, which will bounces, but it breaks whenever we given a sharp blow. And it can also flow like a liquid. So because of it contains the viscoelastic liquid silicon, a type of non-Newtonian fluid, which helps the property or the toy to act as a viscous liquid for a short period of time or a long period of time based on the elastic solid over a short time period. Actually, it was created for the purpose of some medicinal purposes during the World War II by the United States. If you study the silly putty in the Wikipedia, you may have numerous examples of the applications of silly putty in the World War time. Also, one more element which is called the pitch. Very high viscosity, such as very high viscosity. The pitch has a very high viscosity, which appear to behave like a solid, but actually it is a liquid. This pitch is a viscoelastic polymer which can be natural or manufactured, derived from petroleum, coal, and then tar. And in the plants, it is called resin. We may have heard the word resin. Resin is the solid, liquefied, thickened solid, which is called pitch. It is derived from the plant, okay, and the name is called resin. So, some more products made from the plant, like resin, is also like a resin. It is called the rosin. So, these two, silly putty and the pitch, which behaves like a solid, but actually it is a liquid, or we may call it as a fluid. Now we will go to the different types of your fluids. There are so many fluids in the field of fluid dynamics: ideal fluid, a real fluid, Newtonian fluid, and non-Newtonian fluid, ideal plastic fluid, incompressible fluid, or compressible fluid. The first one is the ideal fluid. Actually, there is no ideal fluid. It is a imaginary fluid, which is incompressible in nature, and because it has no viscosity. Because no fluid is in nature, there is no fluid is ideal, because all the fluids have some viscosity. So without viscosity, there is no fluid in the world. So it is an imaginary fluid. The ideal fluid is an imaginary fluid. And the next one is a real fluid, like kerosene, petrol, castor oil, whatever we have seen in our day-to-day life. Everything comes under the real fluid, which have some viscosity and compressible in nature. So all the fluids existing in the world will comes under the real fluid. And the next one is the Newtonian fluid, are fluids that obeys the Newton's law of viscosity. So if it obeys the Newton's law of viscosity, it is called the Newtonian fluid, a real fluid whose shear stress is directly proportional to the shear strain, which is explained in the diagram. Shear stress and its velocity gradient. So if you look at the diagram, you can see the pattern of various flows. Depends upon if the velocity gradient is increases, and if the shear stress is also increases, it will give some pattern of the flow, and based on the pattern, we have seen the structure. So the Newtonian fluid viscosity totally depends upon the temperature and the pressure of the fluid. The examples of Newtonian fluids are water, air, hydrogen, etc. Now, the next one is a ideal plastic fluid. The ideal plastic fluid is a fluid. The shear stress is proportional to the rate of shear strain, and in which the shear stress is more than the yield value is known as the ideal plastic fluid. And then if the fluid is compressible, if we compress a liquid into a gas, it is called a compressible fluid. If we cannot compress, it is called incompressible fluid. And before going to the non-Newtonian fluid, let us see some common characteristics in the Newtonian fluid. So Newtonian fluids do not have any elastic properties. So that is the major difference between Newtonian and the non-Newtonian. So whatever we are seeing, we are discussing here, we can recognize it in our day-to-day life. So the Newtonian fluids do not have any elastic properties. They are incompressible and then unreal. And viscosity is the temperature dependent. So based on the temperature, if the temperature decreases or increases, the corresponding viscosity will increase or decrease. So it entirely depends upon the temperature. Viscosity further depends on the various pressures at which it is found. So if we give more pressure, the viscosity may vary. Depends upon the pressure. The viscoelasticity or the viscosity will increase based on the corresponding temperature. So at a fixed temperature, the viscosity remains constant. So if there is no increase or decrease in the temperature, the viscosity will be remains. So these are all the basic concepts. With the increase in the temperature of the fluid, the viscosity decreases. And the Newtonian fluid, now we will go to the Newtonian, was which will obey the Newton's law of viscosity, the 3 Newton's law of viscosity. Okay, that is the basic differences. Now let us go to the next one. Some non-Newtonian fluid actually are fluids that do not obey the law of viscosity. For example, the oblique, flubber, these are all the examples. Because the shear stress is not directly proportional to the shear strain, which is represented in the diagram. So the study of deformation and the flow characteristics of substances is called the rheology, which is nothing but the field from which we learn about the viscosity of fluids. And the fluid obeys Newton's law of viscosity is known as Newton fluid, and the most common liquids and gases are Newtonian fluids. And then examples, the ketchup, custard, paint and shampoo, honey and toothpaste, etc. And then the Newtonian fluids and non-Newtonian fluids are expressed based on the shearing stress and velocity gradient in this figure. So let us see what is Bingham fluid and dialectant fluid. Okay, let us see. The two major classification of non-Newtonian fluids are the time-independent and time-dependent fluids. As the name implies, the time-independent fluids have a viscosity at any given shear stress and that does not vary with the time. The viscosity of time-dependent fluids, however, changes with the time. Now, this is the table explains the non-Newtonian fluids based on the time-dependent and time-independent and viscoelastic fluids. For a pseudoplastic fluid, if the tau value is less than 1, for example, blood and then milk. Similarly, if the under the time-dependent fluid, this is a thistotropic fluid where the examples are printer ink and then crude oil, etc. Similarly, for the remaining ideal plastic fluid and then rheotic fluids are given based on the mathematical equations. Now, from the figure, the common fluids will always have all the properties based on the time and then the shear stress or shear strain. It will have a common characteristics. It will obey the same characteristics. But the rheoptic and the thixotropic fluids will increase or decrease based on the corresponding time duration. So actually, the thixotropy are the rheopexy, which are nothing but the thixotropic materials where the viscosity decreases as time increases at a constant shear stress. So through this diagram, if you look at the curve structure, we can easily combine the time and the corresponding shear stress. If the time increases and if the shear stress is also increases, that the curve will give you the rheopeptic curve, and if the shear stress is declining based on the time increases, it will give you thixotropic fluid because of its viscosity. Because if the viscosity is increases as the time increases at a constant shear rate, it will give you the thixotropic based on the time. Similarly, the viscosity of liquids decreases and the viscosity of gases increases with temperature. Now, let us see some interesting types of fluid flow. We have seen only the different types of fluids, that is the ideal fluid, real fluid, Newtonian or non-Newtonian. Let us see what are all the different types of fluid flow, the pattern of the fluid which flows between parallel pipes or vertical pipes with a boundary or without boundary, or it is an open channel. First one is a real and ideal fluid. If the fluid is considered frictionless with zero viscosity, it is called the ideal. In real fluids, the viscosity is considered and the shear stresses occur, causing conservation of mechanical energy into thermal energy. So for ideal fluid, there won't be any friction, no ideal flow, energy loss. So the friction is zero. And then mu is also zero, ideal flow, and the energy is also zero. But if everything exists, it is called the real flow. Already I told you that ideal flow is nothing but which is equivalent to the imaginary. If there is no movement, it is called ideal. So it is the real fluid, your friction, energy, a real fluid, everything will exist. Now, the second one is the steady and then unsteady flow. Steady flow occurs when conditions of a point in the flow field don't change with respect to time. So if dou v by dou t equal to 0, it is called a steady flow. If it is not equal to 0, it is called the unsteady flow. For a steady flow with respect to time, the velocity is constant at a certain position with respect to time. For unsteady flow with respect to time, the velocity changes at certain position with respect to time. Next one is the uniform and non-uniform flow. Uniform flow means the velocity is constant at a certain time in different positions. It does not a certain time in different positions. It depends upon the dimensions x or y or z. So if the flow pattern is uniform throughout from the beginning to the end, it is called uniform. And if the non-uniform means, see here, look at the curve in the second diagram. In the bottom and in the top of the channel, or in between any two walls, if it is same, and in the middle of the channel, if the flow pattern is increases, it is called the non-uniform flow. That is because of the different positions. We are calling it as the non-uniform flow. So at a given instant, the velocity is not the same at every point. The flow is non-uniform. Actually, every fluid that flows near a solid boundary will be non-uniform. That is, the solid boundary means the upper layer or in the lower layer, it will be non-uniform, as the fluid at the boundary must take the speed of the boundary. Usually it is zero. However, if the size and the shape of the cross section or the stream of the fluid is constant, the flow is considered to be a uniform. And then the next one is the 1, 2R, and then the 3-dimensional flow. 1-dimensional flow, I think all of you know, it will give a straight line path. And for a 1-dimensional flow means only the flow velocity is a function of one coordinate. And for a 2-dimensional flow means the flow velocity is a function of two coordinates, X and Y. So whatever be the length, see here in the first, if you look at the first diagram, if the channel varies at some instant, okay, but the flow pattern, if it remains constant, if it occupies the entire channel and the flow pattern is not changed from the beginning, or if the expanded form, it is called the 1-dimensional flow. And in the 2-dimensional flow means the flow velocity is a function of two coordinates, and in the 3-dimensional flow, there is the velocity is a function of three coordinates. We have to look at X, Y, and then Z. Now let us see some more interesting. A flow field is best characterized by its velocity distribution. A flow is to be 1 or 2 or 3-dimensional. The velocity varies in the 3 dimensions, 1 to 3 dimensions respectively. However, the variation of velocity in the certain directions can be small relative to the variation in another directions and can be ignored. 1 minute. So the flow field is best characterized by its velocity distribution, and the variation of the velocity in certain directions can be small related to the variation in other directions and can be ignored. And then the next one is the laminar and then turbulent flow. The fluid flows in a separate layers. The no mass mixing between the fluid layers, friction mainly between the fluid layers. And if the Reynolds number is less than 2000, it will form a laminar flow. I already told you that the Reynolds number which occupies the entire fluid dynamics. So let us see here. The Reynolds number classified through this diagram. The Reynolds number classified the flow type according to the motion of the fluid. Low discharge from the starting place and the flow pattern is uniform. Every fluid molecule followed a straight line path and that was parallel to the boundaries of the tube. It is called the laminar flow. If it oscillates like a small oscillation, if we predict the pattern, just like a waves, parallel to the path and that was not parallel to the boundaries of the tube, it is called the transitional flow. And the third pattern, if we cannot predict what type of flow is going on in between the parallel edges, okay, that is called a turbulent flow. Every fluid molecules followed very complex path that led to the mixing of the dye. If we mix some dye into the flow pattern, it won't mix uniformly. Based on the condensation of the dye, it will mix somewhere heavily and somewhere in the loose position. And that type of is called the turbulent flow. But all the flow patterns are only depends upon the corresponding the R value. That is the R value, the Reynolds number. If the R value is less than 10, we can predict that if it is it will be the laminar flow. If the R lies between 1000 to 2000, it is called the transitional flow. If R is greater than 2000, it is called the turbulent flow. So based on the Reynolds number, we can determine what type of flow is going on in the mechanical field. And the next one is the rotational and irrotational flow. The rotation is the average value of rotation of two perpendicular lines in the flow. If the average is equal to 0, then there is no rotation and the flow is called the irrotational flow. So if you look at the diagram, between the lower wall to the middle portion, all the emojis are rotating because of the velocity value. If the velocity profiles, if there is no velocity, the emojis look at the same diagram in the upper part of the channel. So the fluid particles are not rotating because of there is no velocity in the fluid field. So if the velocity is increasing or if the velocity is more from, if there is a velocity, the corresponding flow pattern will vary. So that's why I have used the different emojis which are rotating, and based on the rotation, we can call it as a rotational or irrotational flow. And the streamline is nothing but based on the pattern. If we are having a bunch of transition from one place to another, just like a beam, light beams, it is called the streamline in the field of fluids. Yes, so a streamline is a curve that is everywhere tangent to it at any instant represents an instantaneous local velocity vector. And already we have seen. So this is the corresponding laminar pattern in our real day-to-day life in one factory. And the transitional flow, if you look at the water in the tank, it is visible. So it is a transition. The middle diagram represents a transitional flow, and the third one is the turbulent. First one is the laminar. Now we are going to see the various channels. Open channel, which are classified into two: steady flow, unsteady flow, uniform flow, and the non-uniform flow, which are further classified into rapidly varied flow and then gradually varied flow. So these are all the open channel flows. If you look at the diagram, you can easily grasp the points. The open channel flows are characterized by the presence of a liquid gas interface called the free surface. So the natural flows like rivers, creeks, floods, etc. The human-made systems are the freshwater adequates, irrigation, sewers, drainage ditches, etc. So there are two different open channels. One is the natural one, another one is a human-made. The open channels are classified based on the velocity. If the velocity is 0 on the bottom and sides of the channel due to no slip condition, and if the velocity is maximum at the midplane of the free surface, in most cases the velocity also varies in the streamwise direction. Therefore, the flow is a three-dimensional flow. And further, the flow in an open channel is also classified as uniform or non-uniform depending upon the depth of the Y. And if the uniform flow, it is encountered in the long straight sections where the head loss due to friction is balanced by elevation of the drop. See here, the obstructions cause the flow depth to vary because if you look at the diagram, after some time, the flow is heavily poured into the in-depth pattern, in-depth point where initially it has a wavery structure. Only after some time, the flow is becomes a laminar flow. So this type, if there is an obstruction, that is, if you are having some depth after some section, it with the corresponding, the flow pattern will vary. So rapidly varied flow occurs over a short distance near the obstacles, but the gradually varied flow occurs over a larger distance and usually connects to UF and RVF. So if you look at the diagram, so in between your GVF, RVF and GVF, the flow pattern entirely varies. But after GVF, in between, that is in place of UF, the flow pattern looks like the laminar flow. initially and in the last. The pattern is uniform because there is no variation in the plane in the first and last, but there is a variation. We are having a depth, some instant depth initial to the starting place. If the depth place is somewhere after some time, okay, after 20 kilometers or 30 kilometers, the pattern never be changed because the flow will reach 20 kilometers in a uniform speed. So it won't affect the corresponding rapidity. And then, so if you look at the diagram, the open channel, these are all the open channel examples. So these are all the flow in the open channels. And chute is a channel having a steep slopes, and drop is the similar to chute, but the change in the elevation is within the short distance. So just now we have seen in the previous slide, and this one is the chute, and the next one is the drop. So the next concept is the transport phenomena. Nature of the transport phenomena. The transport phenomena manifests itself in many ordinary processes or activities around you. For example, if you are preparing a coffee, the boiling water pouring into the cup, and then if you mix a solution, everything is based upon the temperature and its viscosity. So the heat usually transfer from the higher places to lower place. Already we have studied in our earlier classes. So based on the concept of our the transport phenomenon, it depends upon the momentum and the energy and then mass equation. These three concepts occupies the entire study of our fluid dynamics. So what are the transport phenomena are nothing but the flow, the transport of momentum and the transport of energy and the transport of mass. So the general equation of the Navier-Stokes equation are the continuity equation and the momentum equation and the energy equation and then the concentration equation. So for an incompressible viscous fluid, it is called delta Q equal to 0, where rho is the density and then constant. And for the momentum equation, the second one, and the third one is the energy equation, and the fourth one is the concentration equation. So if you add any quantity, either heat or chemical reaction or the Soret effect or the Duffer effect, we can study the impact of those constants through the corresponding heat equation and then mass equations, which depends upon the compressible or incompressible fluid flows. So how to study the transport phenomena are study the transportation of momentum, heat, mass through media as governed by various laws of nature. The basic parameters representing the phenomena and the nomenclatures are, there are three methods. One is the molecular level, and the second one is the macroscopic level, and the third one is the microscopic level. So first one is the molecular level. The transport phenomena happening in a molecular scale, the microscopic changes add up to the macroscopic observation. That is in the momentum transport. The molecular momentum is passed from the high velocity molecules to the low velocity molecules. In the heat transport equation, the thermal energy or the heat energy is passed from high energy molecules to low energy molecules. And in the mass transport, the values are transferred from high concentration to low concentration of the species. So the comparison chart is given for those types. The transport phenomena under the equation momentum, the flux and the driving force and diffusivity, the molecular velocity, high to low, and for the heat equation, it is high temperature to lower temperature, and for the third one, mass diffusion equation, higher concentration to lower concentration. So these comparison charts are based on the molecular velocity, molecular energy, molecular concentration about the corresponding Navier-Stokes equations. The molecular transport actually phenomena having some few things in common. That is actually they all tend to transport something. Either it may be a momentum or energy or a mass. All tends to transport something from high to low. So that's why the governing equations looks like similar. These equations are looks like similar because of they are transporting something. Either it may be a momentum or a energy or a mass, but always it is transferring from higher to lower. So that's why they are called the phenomenological laws. So we can also call it as the phenomenological. And then now we will go to so this is the comparison chart. What is transported and how it is transported and what is the effect under the momentum, energy, and then mass. So transported by the molecular motion, the viscosity is mu and the thermal conductivity is K and then diffusivity is D. So all those variables which occupies the Navier-Stokes equations are our viscosity, thermal conductivity, diffusivity, and then concentration C, and then the heat source Q based on the Reynolds number, and then so based on the momentum, energy, and mass equations, the transported by molecular motion, and the next one is the transported in the laminar flow or in solids in one-dimensional. So small elasticity profile, average velocity, momentum flux at surfaces. So what is transported and what is the effect in the first equation or in the second equation and third equation, everything is I have compared through this chart. So the three levels of study of transport phenomena are macroscopic, microscopic, molecular level. No attempt to understand the details of what is going on within the control volume, mainly used for the global assessment of the problem. A macroscopic balance of mass, momentum, energy due to the various inputs and outputs from a control volume. And for the microscopic level, the same study of mass, energy, and then momentum, and attempt to understand the details of what is going on within the control volume. For all those models, we are going to study the velocity profile, temperature profile, and then the concentration profile. But the molecular level it is based on the physical chemistry, theoretical physics, and then complex molecules, extreme temperature or pressure, chemical reacting fluids. So the applications for the molecular levels are will be more interesting, but all those types are studying only the effect of mass and then momentum and then energy transfer, and each of these levels involve the typical length scales. Macroscopic level is based on kilometer, centimeter, or more than that. Microscopic is micron to centimeter range. Molecular level is 1 to 1000 nanometers. So so requirements to understand the subject is the differential equations and vectors and then calculus and the comparison of institution and results obtained, understanding the dimensional analysis. So the mathematical, if you know the differential equations, vectors and then calculus, it will be interesting for you to study about the subject based on the fluids under either a molecular level or a microscopic level or a macroscopic level. The physical interpretation of the key mathematical results get into the habit of relating the physical ideas to equations and comparison of intuition and results obtained, understanding of the dimensional analysis. So that's why, and apart from this, if the fluid is an immiscible or a miscible, there are some common characteristics which is having more applications in our day-to-day life. Nowadays, only the immiscible fluid occupies the entire world, which are having a numerous applications. If the fluids are not mixed, it is called immiscible. For example, water and then alcohol, water and then oil, it is called immiscible. And if there is an immiscible liquid, there will, in between these two, water and oil, there will be a layer, and the layer is called the interface layer. So based on the interface, nowadays the study is extended to the two parallel lines in between horizontal channel or a vertical channel, or it's a slanting channel, or a or it is in the square cubic spear like channels. There are so many channels are formed. Similarly, there are so many flows named code flow, oscillatory flow, and then there are so many flows and so many channels are extended based on the concept of our immiscible fluid flows. And these occupies nowadays the entire world in the field of nanofluid particles, because for nanofluid, if we are having, we can study 1 to 1000 nanometers, but under the nano, for example, in the blood flow pattern in our body, because it is an every neuron is a thinnest tube-like structure. So within that structure, the flow pattern, we can study the flow pattern and the what may be the effect of velocity or the temperature or the concentration. Everything we can study analytically, and then so that's why it will be very interesting if you go through the subject. And thank you all for giving me this opportunity. Ma'am?
Yes, ma'am.
Yes, ma'am. I have stopped my sharing.
Okay, ma'am. Ma'am, 2 minutes, ma'am.
Yes.
Dear participants, any question and answer questions is there regarding today's session? Any questions is there? Okay. Ma'am, it was an informative session, ma'am, for us.
Thank you, ma'am.
I would like to express my gratitude to all delegates who are presented here for attending our 5-day FTP program. This was the third day. I thank each and everyone for your presence. Your feedback link has been posted in chat box. Thank you all. Thank you, ma'am. Thank you for spending your time, ma'am.
Yes, ma'am. Thank you, ma'am. Shall I leave, ma'am?
Thank you. Okay, you can leave, ma'am.
Yes, thank you, ma'am.
Thank you, ma'am. Thank you so much.